Anthony, pronouns he, him, from Virginia. He's a theist. Anthony, I see here you're skeptical of Big Bang cosmology and you want to have a discussion about that. You're with a pro here tonight. So please elaborate a little bit on your question, and then we're going to let Aaron take it away. Welcome.
Yeah. So yesterday I called into the line, and Jimmy and Matt were there, and we got into a discussion about Big Bang cosmology, and they were asking about it, and I expressed my belief that.
Excuse me, Anthony, you need to move your mouth farther away from the microphone.
Okay. Is this better?
A little bit better.
Little bit.
Yeah.
Right.
I've consistent. Yeah. If it's too bad, let me know. Try to adjust a little bit. Anyways, where was I? Oh yeah. So they were asking, and I expressed my belief that I don't really believe the Big Bang. And there are two particular points of question. One is the singularity, from which everything supposedly exploded. And then there was the concept of the expansion of the universe. So I guess my question for you is this. Let me a little bit more. I don't believe scientists can possibly know anything with any level of certainty about the singularity, and I'm quite skeptical about their ability to know anything about a supposed expansion of the universe. So my question would be, what do scientists actually know about the singularity? How do they know it? And the same question for the expansion of the universe.
All right,
well,
I'm going to actually answer it backwards.
No, Aaron, take it away. I was just going to say this is tailor-made for you. Go.
Yeah, and I'm going to answer it backwards, because let's first talk about the expansion, because that is the most direct thing that we can observe. We can actually observe the expansion of the universe by multiple methods. So one is that the observations that were first done back in the 1920s by Edwin Hubble, when he was measuring the distance to various galaxies and finding out, hey, the further away these galaxies are, the faster they seem to be moving away from us. And this was true, pointing his telescope in all different directions. And this has been confirmed by observations for the last century, that there is this nice linear relationship between how far away a galaxy is and how fast it's receding away from us, which is exactly what you expect if you have an expanding universe. The way you can tell this is, one, figuring out the distance to those galaxies. There's a few different methods. The thing he was using was using a kind of star called a Cepheid variable. These are stars that actually oscillate in their brightness in very regular ways, and their rates of oscillation tell you what their underlying brightness is. If you know how bright it is, then you can figure out how far it is away based on the brightness that you're measuring. So that was a method, and there's been other similar methods that can tell us how far away a given galaxy or object is, and we can figure out the speed they're moving away from us by redshift. So the same sort of way with sound, where if there's a train coming towards you, it sounds higher pitch. When it's moving away, lower pitch. Light does a similar thing. If it's moving away, it's redshifted, and the amount it's shifted is depending on how fast it is moving away from us. So we can observe the light from galaxies, and we've done this with a huge survey, and see, yeah, the further away the galaxy is, the faster it's moving away from us in this nice linear relationship, which is a absolute expectation from the general theory of relativity from that Einstein guy you've probably heard of. So when it comes to the expansion, we can directly see it.
Okay, so I think there's a lot of problems with that. So I know that scientists originally proposed the idea the universe is expanding, as you mentioned, in the early 1900s, correct? I believe one of the leading proponents of this, I'm sure it was probably proposed before that, but it gained credibility in the scientific community in like the early to mid 1900s, right?
So to put out the full timeline, so about 1915, 1916, Einstein publishes his general theory of relativity. 1920s, Edwin Hubble has his observations of expansion as looking at various galaxies. By the 30s or 40s, the idea of Big Bang cosmology first comes about with people like Lemaitre, who was actually a Belgian Catholic priest as well as a cosmologist. And he didn't call it the Big Bang. He called it, I think he called it either the primordial atom or the primordial egg. I forget exactly which term he used. Big Bang was a derogatory term added by a different atheist astronomer by the name of Fred Hoyle. Strangely enough, it was an atheist who had a problem with the Big Bang. But times have changed. Then by the, if I remember correctly, it's the 1960s, we then make the discovery of the cosmic microwave background. And this is basically the afterglow from the Big Bang. So basically, as the universe is expanding, then the various gases and dust in there are spreading out and cooling, because in the same way, when a gas expands, it loses, its temperature goes down. And if that's the case, then there should be some sort of way of measuring that gas cooling down over time and that light stretching out as it's crossing the universe. And lo and behold, accidentally, with this radio telescope in the 1960s, they point their telescope in all directions, and there's just this constant hum from the microwave background. They tried cleaning out, thinking it could even be bird poop or anything else, and eventually publish, and somebody else realizes, hey, this is the exact observation that we've been expecting from that Big Bang cosmology idea. And we have now supremely measured that background. When I say supremely measured, we are looking at variations in the temperature of the cosmic microwave background down to the parts of 1 in 100,000. And we can look at those small fluctuations, and they follow statistical rules that actually tell us the rate of expansion, the elements that, when I say elements, I should actually back that up, the kinds of matter that existed back then. So basically, the distribution of all these little variations are what you'd expect from there being dark matter and dark energy, along with a little bit of the regular matter that we're made out of. It also has these oscillations that look like they're most consistent with something that's called cosmic inflation, but this is an add-on to the original Big Bang theory that's probably just going to overcomplicate things. Nonetheless, one of the major key observations was the cosmic microwave background, and it is an absolutely stellar, high precision thing that we have been measuring for decades and decades, and has no other good explanation besides the Big Bang model.
So are you saying, again, I'm having problems with a lot of what's being said, but just this microwave, this background radiation, is this something that exists only in the Big Bang cosmology, or is it something that could theoretically exist in a steady state universe? And what about it seems to me like there's background radiation. Okay, why does that prove the universe exploded from a singularity?
Well, one, it's the
wrong, Aaron,
very direct.
Isn't it the case that the CMB was like a direct prediction that was set out, put in ink prior to its actual discovery and investigation?
Yes,
so
it was.
Oh, go ahead. Sorry.
It was already predicted that. Yeah, so there was already the prediction that if there was this Big Bang event, that there was some time in the finite past where the universe expanded from an extremely small point, then we should see the effects of all that superheated compressed gas basically leaving the afterglow across the entire universe, and it should give a symmetric distribution of temperature across the entire night sky. And the people who discovered it by accident, and there was another astrophysicist looking at that and said, holy shnikes, they found the thing we've been looking for.
Yeah, I think...
Wow. Can you explain this your question about can you explain this with a steady state model? There were attempts to do that once this was discovered. So first off, it's a hallmark of a questionable theory if it doesn't make a prediction, but then somebody can go back and say, oh yeah, it totally fits the data anyways. And the attempts to do that have been very contrived, and they have additional things that they don't observe. For example, the steady state models that would have a cosmic microwave background would also expect that if you look back far enough, you will not see things redshifted from us, but actually begin to blue shift because they'll be oscillating in both directions. Most of the universe will be oscillating away from us, but then you look further back away, then there's some of those oscillations that should be going back towards us and being blue shifted. We've never observed something like that on any cosmic scale. So if anything, observations are against that, and it was kind of a kludge to throw in there in the first place. So as I understand, I don't know of any working cosmologists that hold to this sort of stuff anymore, and the very few that did were a couple old students of Fred Hoyle who hated the Big Bang Theory because he thought it would look too much like creationism. And when I've looked at their papers, they basically just cry out, we're the new Galileo, we're the new Galileo, we're being so persecuted, when in fact everyone's just laughing at their rhetoric.
About the cosmic microwave radiation. From what I understand, it does vary from point to point in the sky, but when you take a complete general look at things, it seems to be uniformly distributed. Is that correct?
It's very uniform. The oscillations in it are fractions of a degree in temperature, so they are very, very small oscillations. Sometimes, like, you have to be measuring them down to like to 1 part in 100,000 to actually have noticeable difference from one part of the sky versus another.
Okay. See, when I think about an explosion, it would lead to significant variations from location to location within the universe of this variation, but in a steady state, it would have time to balance out. So, first of all, they claim the existence of the background radiation, this proof itself. I think there's a lot of things out there that could be, creating or causing this, and it isn't necessarily explained by a singularity expansion. But I haven't seen any proof.
What would be an alternative means to explain the CMB?
There's a lot of things in the universe that emit various types of radiation. I think we're just beginning to understand a lot about the different celestial bodies that are out there.
You're talking about individual objects that might, but here's the thing. Individual objects very far away are going to be point-like. We're talking about something filling up every single square steradian of the nighttime sky in all directions evenly. That is not what you get from a whole bunch of point-like sources.
But over time, you would expect it to fill the entire universe, even if it's originating from various points.
You would, but you would also expect concentrations near those sources, which is not what we see at all. In fact, it is like, forgive me if I mess this up, Aaron, but like it's pretty as about as uniform gets.
Yeah, like I say, it's extremely tiny fluctuations. In fact, the level of smoothness was actually even considered a problem with earlier models of the Big Bang, which is one of the things that cosmic inflation helped solve, because it actually further flattened out any sorts of oscillations or variations. Now, like I say, inflation is itself, and saying an add-on sounds like it's just kind of a kludge, but this was an additional thing that was proposed by Alan Guth back in 1980 at MIT, and since I have an affiliation at MIT, woohoo. But Guth's idea is basically an extremely early exponential expansion of the universe in like the very earliest moments there that actually helped solve a couple different problems with that cosmological picture. And I will say that inflation doesn't have the same level of universal regard as the Big Bang itself, but as most cosmologists, and they'd probably say inflation is more likely right than wrong, though we're still trying to get more definitive evidence one way or the other about that. So I'm just trying to stick with only the theory that's universally accepted by cosmologists.
Right, the one that's tied to the CMB, which, as the three of us have discussed already, has no other existing alternative explanation for its ubiquitous presence. Right, like it is the singular hypothesis, the single theory that stands above all others at this moment in time, and it's not even close.
It's also worth. In fact, I should note another feature about this is that it's not just radiation. It's also radiation 100% consistent with black body radiation. It is consistent with something that was hot and that has cooled down to 2.7 Kelvin, which is what we call damn cold. That's 2.7 Kelvin. That's 2.7 degrees above absolute zero. So it is basically about the coldest you will ever experience, even with modern tech. You have to go to CERN to even have any large-scale thing below 2 Kelvin. And even there, it's hard to maintain. So the fact that you get black body radiation across the entire universe in all directions with only tiny variations that seem to also correspond to like the tiny bits of clustering of matter that would lead ultimately to things like stars and galaxies is supremely expected from a Big Bang model, and it's only with a bunch of kludges and other observational issues can you get that to fit with a steady state model. I should also note a few other things. First off, if we look further back in time, by looking further back in the sky, because the further away you look at things, that's further back in time because of the finite speed of light. We look back there and we can look at the chemical composition of things and we see, hey, it's mostly hydrogen and helium. There's almost none of the other heavier elements, which indicates that, hey, their fusion process had to build that up more and more over time. That's not something you would expect if this were this just continuous steady state for the universe. You would expect a little bit more steadiness across that. Also worth noting that the creation of hydrogen, helium, and tiny trace amounts of lithium are the sorts of things that you would also predict from particle physics if you started with an extremely hot, dense state that the early universe would have been in, that basically in those first couple of minutes that you would have developed and had those lighter elements. And it's kind of a crazy thing. Lithium, number 3 on the periodic table, virtually all the lithium in the universe was created at the Big Bang. It's actually not something that gets normally created in atomic fusion in stars. So strangely enough, the lithium in my computer right now for the battery, almost all of it came from the Big Bang. And otherwise, we don't have an explanation for like nuclear processes that would produce it.
I don't. Okay, so again, there's so much to comment on. To me, this might be my ignorance because I'm not an expert in this field, but I feel like the uniformity of the background radiation is more consistent with a steady state model than a Big Bang model. And again, that's maybe I'm yielding that may be my ignorance. I don't see.
I think.
Okay, go ahead.
The most straightforward way to show that notion is incorrect, and I understand where you're coming from, like intuitively speaking, like, but science rarely follows our intuition or common sense. And from our point being so tiny in the grand scheme of how large the universe actually is, this problem of common sense leading us astray is even more exacerbated. But the model again of steady state versus the Big Bang as we understand it, right? Both of these models had specific predictions before we were able to investigate things like the CMB, right? Before we even knew about it or had instruments that were capable of picking it up and knowing what we were looking at, right? And yet, the CMB has been discovered, analyzed, right? And it matches only the Big Bang to the exclusion of steady state, which has, as Aaron outlined, tried to accommodate it and failed on multiple different fronts. That, we can go back and listen to what Aaron said later to hear each of these failed predictions and failed accommodations. So at this point, I don't think that you can say, like, well, I still feel like steady state better accommodates it, because it doesn't, by the admission of the people who came up with it, because it wasn't included in their original predictions that the CMB would even be a thing.
I should also add that I think one thing that might be leading Anthony astray is that he refers to the Big Bang as an explosion. And I think that is driving your intuition in erroneous ways, because more correctly, we should be referring to the Big Bang as an expansion from an earlier state, and not even necessarily a singularity. If there is even singularities at all, is arguably not the case. Most people don't think singularities even exist. But nonetheless, if you instead think of it as an expansion, then you're thinking of the expansion of a gas. Well, an expanding gas is going to expand pretty much evenly. In fact, the only reason you get any sort of clumpiness at all in some sort of expanding gas is because of another force being involved. And it's the force that, keeps my feet on the ground, gravity. The reason we have any clumpiness at all is ultimately the additional force of gravity that in some cases can overcome the repulsion from gas being too hot to be pushed apart. And that's kind of the fundamental thing that pretty much all of astrophysics will get down to just dealing with two things: hot stuff and heavy stuff. The hotness basically causing an outward expansion, and the heaviness from gravity that tries to pull things and clump things together. If you don't have gravity and you just have an expanding gas, you're going to have pretty much a perfectly even mixture everywhere. The only reason we got any clumpiness is our friend Big G, as I like to call him.
Okay. Well, okay. Let's go with that. I find that an interesting notion about an expansion, and I was having a conversation with someone years back about the quote Big Bang. They made an interesting comment, and they stated that, well, the universe is expanding, and then a question immediately arises: expanding into what? What does it mean, actually, that the universe is expanding? Because supposedly all of space-time was condensed within this alleged singularity. So what exactly is outside the singularity and outside of space-time into which the universe is expanding? Have scientists tried to answer that question? I'm sure they have, but what are there theories?
Before we move directly onto this next point, I want to put a cap on it, right? Like on the CMB thing, I feel that you have your work cut out for you here, Anthony. Like if you don't want to accept CMB as a successful prediction of the Big Bang, or maybe you do and you just want to look more into it, I think that's like, as far as that portion of our conversation is where you should go next and go and see, okay, like what did steady state predict? What did the Big Bang predict? And then how does each line up with our observations with regard to CMB? Are we good on that?
Well, we're not, because from what I understand,
okay,
the cosmic, well, Aaron mentions, was the idea that the farther we look back into the universe with these space telescopes, the less developed the galaxy should be. And this is something I brought up with Jimmy yesterday, which is that recently, and when I say recently, I mean within the last year or two, the James Webb telescope was able to peer farther into the universe than ever before. And if I remember correctly, the scientific community was amazed to find that the farther we looked, the universe seemed to be at a much greater state of development than had been predicted, according to, statements made by Big Bang proponent theorists. So it seems to me that the evidence is kind of trending against the Big Bang cosmology.
So
I'm going to
Anthony,
have to hop
I know
on that
exactly.
and just squash that hard. I'm going to squash that hard, because every headline that has said that has been just sensational nonsense, because not a single scientist who has been publishing these results say anything about this breaking the Big Bang. What it is basically saying is our models for the development of galactic formation need revision. And the question is, what thing is it that our models are not accounting for well? Is it that we are using an incorrect model for dark matter, for example? That is still something that is very mysterious and theoretical, trying to explain it in terms of different forms of gravity. So like there's modified Newtonian dynamics, or MOND is a candidate that is used. If it is a particle, which many particle theorists try to explain dark matter with, then what kind of particle and what other properties might it have? How much does it cluster? What sort of geometry does it spread around? Those are the sorts of questions that come up. Or the questions might be, when we're doing our various computer simulations, are there issues with the way that we're running those simulations? Are we dealing with heating and cooling methods of the gases correctly? This is something I even remember from some of my undergrad research. Hey, we're seeing these things with the galaxies, and our computer model isn't matching with this. If we add this additional variable, does it help things match better? In other words, it might be that a bunch of the other steps in our very complicated things may not be working out so well in those particular cases. But it's still worth noting that even those galaxies that we're seeing basically them clustering up and getting bigger faster than might have been initially expected, but they still have basically the primordial abundances of the elements. We don't look back 13 billion years into the past and find stars that are like big chunks of uranium or anything like that. No, they are, in the parlance of astronomers, low metallicity objects. And for astronomers, anything higher up in the periodic table than helium is called a metal, because astronomers don't want to be precise, just to piss off the chemist. You aren't seeing the sorts of things that would say, hey, there's an extra 100 billion years of history here. It's basically saying, hey, our rate of galaxy formation models aren't right. This is not an argument against the Big Bang. This is an argument that we need to do better simulations. And I would like some more grant money to run some simulations, please.
So I want to actually add on to that because I remember explicitly, I argue a lot with creationists, young Earth creationists in particular. It was Jason Lisle that was publicizing and popularizing a lot of this, like, oh, scientists are saying that the Big Bang is in trouble, whatever. Look, I'm not an astronomer and I'm not a physicist, but I can, stumble my way through these types of papers. None of these papers mentioned the debunking of the Big Bang. It was exclusively pop science coverage, and usually it was pop science coverage that was talking about, as Aaron mentioned here, early galactic formation, like early formation of galaxies. Then, most recently, additional work has come out on these observations about these galaxies, they're so young. Some of them are younger than we expected. They are absolutely positively not the same age as the galaxies that we are surrounded by now, which is effectively what is required under like a steady state or a young Earth creationist perspective, which would say that all of the galaxies were created roughly at the same time. This is completely contra, and this is why, like, I've not seen Jason Lisle, at least the young Earth creationist, elaborate on these new findings. He's just been sticking with the whole, when they first found out, they were shocked. No, it was surprising for sure that the galaxies were older than expected, given the time period that we were looking at. But they were not the same age as adjacent galaxies today. They are significantly younger, which serves to reason that the galactic model needs to be revised, but not entirely thrown out. It's a clock that's off by a few ticks.
In fact, I'll throw in one other thing that these models have not generally included, because it's been a relatively recent theory, but another method for the formation of black holes and producing supermassive black holes. That in the very early universe, the only kinds of stars that you can form are the most massive kinds of stars possible. Again, because the gases are warm, you need even more mass to actually have enough gravitational force to defeat that. This is something called the Jeans mass or the Jeans density, if you want to look in the astronomy terms for that. But you basically realize, hey, these stars are so big that at their cores, they could actually maybe start forming black holes, or even have black holes at their core, keeping them, quote unquote, alive rather than atomic fusion. And then you have gigantic amounts of mass producing these supermassive black holes, and we find, hey, supermassive black holes are at the cores of the vast majority of galaxies. Maybe this is something we need to better understand the seeding of galaxies in the first place, which just means, hey, we just discovered some new observations that might lead us to a completely different formation of black holes, which would be absolutely awesome, but it doesn't throw out everything else that leads us to Big Bang cosmology.
Okay. Well, I also had a question. When we talk about the redshift and objects in all directions appearing to move farther away from us the farther they are out, and these ideas of the farther we look out from Earth into the universe, the younger we should see it. Doesn't this kind of presuppose that the Earth is in the exact center of the universe? Like, how do we know we're not in the younger portion of the universe? And
I see what you're thinking there, but the thing is, whether we were observing here in the Milky Way galaxy, the Andromeda galaxy, or any other one, everyone will be seeing the same sort of effect, that the objects further away from them are going to be moving faster away from them, because if you can imagine some sort of membrane that's being stretched, everyone's going to have the same sort of observations. Everything close to them is barely being pulled away, and the things far away are being pulled away really far apart. So we would get the same sorts of observations whether we're here on Earth, Alpha Centauri, Andromeda Galaxy, or any other galaxy you care to name.
Okay. So as far as the expansion, we would see the same thing no matter where we go. But when it comes to the age of these various universal bodies and galaxies and things, we could potentially be on the outside of things in the younger part. We don't know where we are in relation to everything else. So
Anthony, I've heard this from Jason. I've heard this from Jason Lisle before, right? Like this is like a pseudo. Well, it's kind of adjacent to like the white hole cosmology, where like God creates everything in sort of the middle, and then like creates the Earth and things in the middle, and then everything else is kind of expanding outward from that. But the problem with that is we're receiving light from stars right now that are over 6,000 light years away, right?
So-
we are. That cannot be the case if the Earth is 6,000 years old. This is not possible unless God is inherently deceptive and is creating light in transit, which is, interestingly enough, something most creationists would reject because it is, in fact, deceptive. So
Yeah, I
there
agree.
is no way to look at stellar bodies and interpret them as being within a young Earth time frame. I don't know if that's where you're coming from, but I wanted to put that
No,
out
it's
there.
not. Yeah, I don't believe. Yeah, I agree with everything you just said. I don't.
Right.
Yeah,
So-
the universe is older than six. It's in a steady state model. The universe is actually infinitely old, and it kind of recombines and reprocesses itself infinitely, and everything's in a cycle. But so that's kind of the idea, is that the physical universe is actually infinitely old. And there's logical reasons for believing that would be the case. And the variations we see within the universe are the result of the motions of the celestial bodies interacting with each other over time, breaking down. And it gets interesting and to realize that where God's intervention comes in all this. But my point was that when you were talking about looking into the universe and assuming that the farther out we look, the younger the things are going to be, that presupposes the idea that we're in the exact center of the universe. Because if we're not in the center of the universe and we turn in a certain direction, we would expect things to be older than we are, and we look in the opposite direction.
The observations of the further away you look, the further back in time you're looking, is going to be true anywhere in the universe. That is going to be independent of your location, because Andromeda Galaxy is about 2.5 million light years away. So when we're looking at it 2.5 million years ago. If there are aliens in Andromeda looking back in our direction, they're seeing the Milky Way as it was for them 2.5 million years ago. So if we're looking at Andromeda now, we're seeing it 2.5 million years ago. Andromedans looking back at us, they're not even going to see Homo sapiens. We're not even around yet. Erika, you're going to have to tell me which hominids they would see, or what
you're
kind
right.
of monkeys would have been around to be seen.
Homo habilis and Homo ruralfensis, thereabouts.
So
I think you are absolutely right. So I was kind of wrong on that point, but I do think that seems to me that the explanations don't take into account the idea that depending on which direction we look, I guess that actually does make sense. Yeah. So whichever direction we look, things will appear to be younger. Okay, that makes sense.
I think this has been a super enjoyable conversation, but unfortunately we still have a lot of other callers on the line, and I want to get through as many of them as possible. Maybe you can call again next time. Maybe what you can do is look into some of the stuff that we've talked about today, and then if you want to talk to Aaron more, I am sure he will be back. And then you can come back guns blazing with I read up on this and I'm ready to put the thumb screws on him. Does that sound okay?
So
all right, thank you.
Wonderful.
Come
Thank
back
you
with
very
the Friedman
much.
equations so we can discuss those.
Yeah. No, please don't do that. Bye-bye, Anthony.
I'm
Take
sorry.
care.
Thank you.
Come on. More math, more all the time.
No, less math, less physics, less chemistry, more squishy biology. I thought that was a productive conversation. I learned a lot, actually. Every time we were on here, Aaron, I learned a lot because my cosmology is not great. So I appreciated that, seriously.
Hello, I'm Jimmy Snow, Pokemon Master and Executive Producer on The Line. Would you like to support a specific show on The Line or The Line in general? There are special tiers on our Patreon and in our channel memberships. You can do just that. By the way, you could consider leaving a super thanks down below. You could also subscribe, and leave a regular comment. All of these are great. Now, I'm going to get back to crushing loneliness, but while I do that, why don't you check out one of these?